You talked about the carbon cycle, so you probably talked about we generate just under 50 billion tons of CO2 each year, put it into the atmosphere. So let me help you put that in perspective. So when we capture the carbon, there are a lot of people who say, can we convert this carbon into plastics or fuel or something like that? So from the fuel standpoint, there's a whole area of science called thermodynamics, and basically thermodynamics is the study of how you move energy around. And the basic principle is this: is if you imagine that all things can be put kind of prioritized in priority in terms of how much energy energy content they have. At the top of that would be nuclear fuels, for example. We go down this priority level, and when we get to CO2, we are at the very bottom of the deepest part of the well of the energy spectrum. And so to move that carbon back up the spectrum where we could use it again, use the carbon again, will take you have to invest a lot of energy to move it back up that energy spectrum again. And there's a fundamental rule that says the amount of energy that you have to put back into turning carbon back into a fuel, for example, will always exceed by a significant margin the amount of energy you'd be able to get back out of that fuel again if you were to burn it again. So the idea of turning CO2 into a fuel and then burning it again is you can kind of see that that's a perpetual motion kind of an idea, right? You really can't do that. Now, what about turning it into plastics or some other thing that we use carbon for? So the same energy argument is still there, but there's an even larger market argument, and that is, if you look at the total amount of CO2 that we are putting into the atmosphere each year, and compare that with the sum of all of the carbon that we use in all carbon-based products that we produce, that we manufacture. So go back to the base chemicals and say, how much are we putting in polypropylene, polyethylene? There's over 30 times more carbon going into the atmosphere in the form of CO2 every year than there is going into the form of plastics or any other manufactured chemicals. So if you wanted to find a way to turn this carbon into something, the energetic hurdle is huge, but the market hurdle is even bigger. You'd have to find some market for carbon that would be 30 times bigger than the sum of all manufactured chemicals that we produce. That's not a very practical reality. So there are things you can do with the carbon dioxide. You can use it for enhanced oil recovery. So you pump carbon dioxide into an oil well, and it helps to move the oil back out of the oil well. It helps to increases the productivity of the oil well. It's actually fairly valuable in that sense, though people will pay you $40 a ton for the CO2. Thank you. So there are several things you can do with it, and those are large enough markets that if you do them locally, that would make sense locally for a power plant. But globally, the amount of CO2 we produce will swamp any market existing or conceivable in the future in terms of where the CO2 is going to go. So most of the CO2, if we capture enough CO2 to be able to put it in to make a difference to climate change, we've got to find a place to store most of it, and most of that will end up being underground in a saline aquifer, they're widely available and they're very safe places to store the CO2. But there won't be a lot of the amount of CO2 you'll be able to reuse is fairly small. So this just shows the CO2, the global energy-related CO2 emissions and where they come from for the most part. So mostly coal, a little bit natural gas, and liquids would be mostly transportation fuel. And then CO2 isn't the only greenhouse gas, so this is the other greenhouse gas sources. So the energy ones are at the bottom, but as you climb up there, you can see the effects of agriculture and forestry and waste and buildings and other kinds of things. So the total CO2 equivalent is about, in 2010, is right around 50 billion tons of CO2 being produced each year. So probably last week you studied the carbon cycle and found out that approximately half of that actually ends up going back into the oceans and into the flora and fauna of the planet, and the other half accumulates in the atmosphere. So roughly half of that is piling up in the atmosphere. We're now at about 400 parts per million CO2 in the atmosphere. That's higher than we've been in any history by any normal sense of the word. There are times in the very ancient history of the Earth when the CO2 content's been higher, but that was eons ago. And so that's what's scaring everybody, is the potential of that and the potential impact on climate change. So I'm not going to rehash all of that, but I will, since there are probably several people interested in policy. This shows the per capita emissions of CO2 for different parts of the world. North America is at the top, but declining fairly significantly, and has been in decline fairly significantly. So per person, we're actually, in North America, we're consuming less CO2 per year than every year. We're consuming a little bit less. In the last few years, it's been in relatively significant decline. That's in part because we actually are using less energy for the things we do. We're driving less than we used to. It's in part because we were just coming out of a recession, and the recessions always have a big impact on energy utilization. They're very closely tied to the economy. But actually, the biggest part of it is the change in utilization. So switching to less carbon intensity things. So in about the middle of this graph, you can find Europe and other places that are reasonably developed, and at the bottom are the places that are lesser developed. So that's where the CO2 is coming from, and this is the historical carbon balance that I talked about half of it going back into some form of, back into the earth in some form, and half of it into the atmosphere. And these are the markets. So how much of the CO2 do we have to capture in order to make a difference in the climate? And this is pretty recent data from the United Nations. They're the United Nations energy gap, they call it, their energy gap analysis. And so you can see in 2012, the last data they have there, they estimate we're emitting about 54 gigatons of CO2 per year. To get to a place where we've stabilized the planet at a 2 degrees C target, which is the target that a lot of people, that is, the temperature rise will be limited to 2 degrees C, we have to reduce the CO2 emissions down to about 22, roughly, gigatons per year. So at 22 gigatons per year, the Earth has natural cycles that can manage that and maintain the temperature at just about a 2 degree rise. But we have to keep it at 22 gigatons per year for 100 years. So here's some other fairly staggering data. So how much is it costing right now to capture this CO2 and do something with it? And these are different kinds of captures that people have advertised. This is the cost of doing the capture. This isn't, so if you were to actually to do this commercially, presumably there would be some profit and operating expenses added to this, but roughly $80 per ton of CO2 that we're capturing. Now, if you remember, we talked about reducing the amount of CO2 emission by about 25 gigatons per year. So even if we only do half of that, if we do 10 gigatons per year at $80 per ton, we're talking about $800 billion a year that it's going to cost to do this. If you do the full 25 tons, we're up at $2 trillion a year. To help put that in perspective, the entire energy industry is about a $5 trillion a year. That's all energy companies combined, is about a $5 trillion a year enterprise. So this is not a small undertaking. This is going to be a huge, huge issue. So what can we do about it? First, I'll give you just some at least my global view of how things are going to happen. So cryogenic carbon capture is not only possible, it's essential for us to solve the energy problem. It's got to be a major contributor to this issue. And what we need are revolutionary, not evolutionary, changes to technology. And I'll show some of the technologies that people are trying to commercialize right now, but they simply are inadequate to this task. They are too expensive and they are too inefficient, and they just will never be implemented in the forms that they're in right now. But there's also there are limits to what we can do with this carbon capture technology. So we could probably reduce by roughly a factor of 2 our carbon emissions, but reducing them by a factor of 3 would be extremely difficult. So this isn't a panacea that's going to address everything, but it can address some of it. So even if you don't buy into the kind of market-based philosophy that a big fraction of our state buys into here, it is essential that whatever you do it in combination with the markets. And so just as an indicator of that, well, maybe one of the vivid indicators of this is, I just went through this analysis just a couple of weeks ago. So over the last approximately 25 years, there have been there have been 750 million people who have moved from poverty into the middle class, globally speaking. So most of us in this room, if you think back over the last 25 years, and if you're conscious about the economy, it's been a pretty rough couple of decades. But globally, that's unprecedented. It's completely unprecedented in terms of addressing wealth. Essentially all of that movement from poverty into the middle class has come by virtue of economic transformations in developing countries. So prior to this 25 years, there were a lot of humanitarian and NGO kinds of organizations who worked very, very hard at trying to address poverty issues and made almost no progress over that whole time period in terms of the percent of the planet. So until recently, about 60% of the planet lived in abject poverty at $1.25 per day, roughly spending capacity. And that's now dropped to about 35 to 40%. In the history of the world, as far back as people can go, there's never been an economic transformation like that. But none of it was done with the intention to address poverty. So almost all of that change came because the market moved to China and Southeast Asia, not so much into Africa. Africa is still suffering significantly. And a lot of people ended up finding economic jobs and moving into a much better standard of living than they had before. And that's just a testament to how powerful the market can be in creating change. So if you had told somebody 25 years ago that we're going to make this huge transformation, recognize this is more than twice the population of the United States that has moved significantly economically. And if you had told somebody 25 years ago that that was going to happen, they wouldn't have been able to imagine how that would ever be possible. So getting the markets involved in this and making sure that we have market support is essential. There is in the carbon capture community, if you're familiar with it all, we've kind of come to this default of we're going to capture 90% of what comes out of a power plant. In my view, that's the wrong number. So we have, if you remember the carbon numbers from earlier, roughly a third of the total CO2 emission comes from automobiles. It's going to be much cheaper and easier to capture carbon from a large stationary source like a power plant than it will be from a mobile source like an automobile, or imagine an airplane of some sort, trying to capture the carbon from that. So we should be capturing everything we can from the stationary sources, because there's probably very little we can do about airplane CO2 emission and even large truck CO2 emissions. Well, there actually are some things we can do there, but they're much more difficult than these. So 99% is the right target, I think, or more. So there's been a large transformation in the United States, roughly, mostly limited to the United States right now, but it could happen in other places in the world, moving toward natural gas. Natural gas has become very cheap again. Just want to point out that if we were to convert all of the power plants in the world to natural gas, we would not have made we would have made a significant change in CO2 emissions, but not nearly as big a change as we need to make to address the climate change issues. So natural gas is a step in the right direction and a partial solution, but it's not the solution to this problem in terms of what's happening all over the world. So a couple of other things I want to point out is I'll show you some economic data in just a minute, but in most power plants for coal power plants, a little over roughly half of the cost of generating electricity from a coal-fired power plant is the cost of building the power plant, and the other half is paying the salaries and paying for the fuel and stuff like that, about 40% actually. For a nuclear power plant, about 90% of the cost of generating nuclear power is the cost of building the power plant. Only less than 10% goes into the cost of the fuel and the people that run it and those kinds of things. And so when you think about that, if you develop a technology that requires that you build in a completely new power plant, you're going to make the cost of carbon capture prohibitively high, because now not only do you have to build the technology that you have in mind, but you also have to build a new power plant. And in most of the places in the world, the places that are generating most of the CO2, which right now is China, followed by India, and then by the United States now, they have just built a huge fleet of power plants. Well, they are still building a huge fleet of power plants. And the idea that they're going to tear down these new power plants and rebuild a different kind of a power plant is just not practical. So you need to find some sort of a technology that you can retrofit onto an existing system, and you don't have to tear down the existing systems in order to make this work. So with all that in mind, let me talk about some of the options. So the most mature carbon capture technology is an amine-based or a solvent-based system. I'm going to step away from here and talk. Tell me if I'm not talking loud enough. So the way this works is you take the exhaust from a power plant. So just to put this in perspective, the exhaust duct, the channel through which the exhaust moves in a coal-fired power plant would be about 3 times as high as this room and twice as wide. And so this is a lot of gas coming out of this power plant. So you put that in here, and you have a chemical. And these chemicals typically an amine kind of a chemical that absorbs CO2, and so the gas bubbles up through this chemical. The chemical is in water, dissolved in water, and it absorbs the CO2 and pulls the CO2 out with the chemical. And then you go to another tower where you spray the chemical with the CO2 in it, and you heat up the chemical with the CO2, and that drives the CO2 back out of the chemical and back into the gas phase in a classical absorption. So they call this an absorber column, and this one's called a stripper column. And so then you produce pure CO2 over here, and you can use that for enhanced oil recovery or put it in the ground or whatever you're going to do with the CO2. So this is the technology. This technology actually had its origins in separating CO2 from natural gas. When natural gas comes out of the ground, frequently it has way too much CO2 in it to put into a pipeline. So they separate the CO2 out of the natural gas before they put it in a pipeline. And then people modified it to make it work for these exhaust systems. Another system that is pretty clever, this one we call Oxyfuel. So usually we burn things with air, and most of air is nitrogen. But if we burn something in pure oxygen, then the oxygen would form carbon dioxide and water. And the carbon dioxide, we can condense the water fairly easily, and that would leave us with just carbon dioxide, so then we don't have to separate it from everything. And that's a process called Oxyfuel. So that part of it is pretty good. The difficult part of that is separating the oxygen from the air so that you can get the pure oxygen in the plant. But the way this would work is you'd have an air separation unit that would pull essentially pure oxygen in here, inject that with the fuel, and then just condense the water and pressurize the CO2 at the tail end of the plant. So those are the 2 leading technologies that have a lot of attention. Another one is gasification. This one is turning coal or some other solid fuel biomass, sometimes even natural gas, into carbon monoxide and hydrogen, and then using the carbon monoxide and hydrogen. One of the interesting things you can do with this is you can then use the carbon monoxide and hydrogen and stitch together molecules of transportation fuel like diesel or gasoline or things like that. Or you can just burn it in a gas turbine and make electricity. So gasification is another technology that potentially would lend itself to CO2 capture. So this is the problem with these technologies. So the first is the impact on efficiency. So what you see on the left over there are typical efficiencies for power plants these days, in this case coal-fired power plants. And what you see on the right is what their efficiencies would be in the best case scenarios if you implemented these technologies. And so if you look across there, you can see those efficiencies are dropping by about 30%. So the CO2 separation process consumes 30% of the output of the power plant. And that's an enormous parasitic loss to have to pay for something. To put that in contrast, everything else that the power plant does consumes about 3% of the output of the power plant. So the normal parasitic loss would be 3 or at most 4%. So, perhaps to some people, more importantly, this is what the process does to costs. And so you increase the cost of electricity by about 80% by implementing these technologies, depending on how you implement them. So that cost change is actually less of a concern to me than the energy change, but both of them are pretty daunting. Now, if you had to rebuild the power plant, in addition to building the technology that's going to capture the CO2, instead of an 80% increase in electrical power in the United States, in most cases you'd be looking at about a 500% increase in the cost of electrical power. So that's why these bolt-on technologies are so important, is that you want to do something that you don't have to rebuild the power plant. So I'm going to tell you now about a process we've developed here. It's been reviewed thoroughly by the Department of Energy, by a lot of experts all over the world, and it shows promise so the Director of Research at EPA wrote a letter that he copied me on to one of the DOE big shots the other day. He says this is going to change everything about the climate change. So we call this cryogenic carbon capture. One of the things I love about this is if you sit down with an engineer, in fact I did this just today, a very brilliant engineer from chemical engineer. I said, I'm going to tell you about this process. When I first tell you about it, it's going to sound crazy. You're going to say, this is insane. And within 10 minutes, you're going to say, this is obvious, that this is what we ought to be doing. So it's one of those kind of things that not at all intuitive until you think it through. So what we are going to do is take this flue gas that comes from a power plant, and we're going to cool it down to the point that the CO2 condenses. And when CO2 condenses at atmospheric pressure, it condenses as a solid. It goes directly from a gas to a solid, a process we call desublimation. And so it basically forms CO2 snowflakes, much the same way that water goes directly from a vapor to a solid in a snowstorm. This CO2 is going to go from a gas to a solid, and going to create one of the biggest blizzards that you can imagine. So it's just thick with CO2 flakes, not snowflakes. To get that to happen, we have to cool it down to about a negative 120 degrees Celsius. If at 90% capture. 99% capture takes about a negative 130 degrees Celsius. So you remember how big that duct was that I told you about. So if you can imagine the refrigerator that has enough refrigeration power to take that much gas and cool it down that cold. What makes this make sense is that unlike a normal refrigerator, so if I compare this, for example, to your air conditioner, if we designed an air conditioner the way that we designed this, your air conditioner would be extraordinarily efficient. However, the air conditioner would produce air that's at the same temperature that the air came into the air conditioner. So it would go to a very cold temperature in the middle of the air conditioner, and if you could derive a lot of comfort out of the idea that this air just a few moments ago was very, very cold, then it would be an effective air conditioner. So we don't deliver anything at a cold temperature here. We warm everything back up to room temperature, and that means we can use all of that energy that we use to cool things back down with. We can use that energy in warming that material back up to room temperature. We can cool down the next batch of material that's coming in the front end, and that makes this process way more efficient than what normal calculation would suggest that it is. So when we do that, I'll step through this again. So the flue gas comes in the duct here. First we take the water out of it. Water, by the way, is a huge issue in energy. So we actually pull more water out of our national water supply system to generate electrical power than we do for crops. That might surprise you. Agriculture uses less water than power does in the United States. So we recover this water, the water that's in the flue gas. We actually will use it on site to decrease the water demand of the power plant. But then we go through a series of, this is what I love about engineering. So we're not very elegant about how we talk about equipment. So there's actually a whole series of boxes here, and their purpose is to exchange heat. You want something cold and then something hot. You want to make the hot thing cold and cold thing hot, and we call them heat exchangers, of course. So, and so you go through a whole series of heat exchangers. The radiator in your car is an example of a heat exchanger. And so we go through a bunch of heat exchangers until we get this so cold that we have this flurry of CO2 particles, and now they're solid particles, and they're trained in gases, but it's really easy to separate a solid from a gas. And so we go to a gas-solid separation, and then we pack these snowballs into, we try to squeeze all of the air out of it when we can to make sure that we have just CO2 and not any air in here. So we compress the solids, and then we warm everything back up again in this heat exchanger. In the process of warming up, the CO2 is now at high pressure. So instead of going back to a gas, because it's at a high pressure, it goes to a liquid and forms liquid CO2. So this is dry ice at this point. We melt the dry ice and form liquid CO2 and deliver a high pressure liquid CO2 stream that you can pump into the ground, destroy the ground, or was used for enhanced oil recovery. And the rest of the gases, which are mostly nitrogen, come out of the process here. So that process consumes, let me see if I've got I think I might have left the economic slides out here. So this process consumes half of the energy of the other ones that I talked about. So 15%-ish, 12 to 15% parasitic load on a power plant to run this process. So by itself, that's still a staggeringly high number, but that's a much, much more manageable number than 30% parasitic loss. And it's actually quite close to the theoretical minimum amount of energy that it's going to take to do this separation. It's probably as close as any real system can get to that theoretical minimum. And it also costs a little less than half as much as the other processes. It's a bolt-on technology and has several other advantages that I'll talk to you about in a minute. But this is still an expensive, costly technology. 10%, 15% parasitic loss is a lot. And like I tell the people I work with, both here and at the company, the reason people are so excited about this technology is because we are in an ugly contest. And we are the least ugly of a bunch of very ugly choices that people are looking at for doing this CO2 capture. And so this process is, one of the other really important things is, if you go back to the very beginning part of my talk, we talked about how do we get energy systems that really make sense. So the two greatest needs that the energy industry has right now, that at least the electrical power industry has, are carbon capture, in my opinion, and energy storage. So if we could, remember those windmills we talked about, so at nighttime windmills spin up and they generate a bunch of electricity, and truthfully that electricity mostly causes havoc on the grid. It's not in high demand, and since you don't know if the wind's going to be blowing, when you build the wind farm, if you build a 100 megawatt wind farm, you've got to build a 100 megawatt fossil power plant. You typically also, because if the wind isn't blowing, you've still got to be able to generate that power. So you end up building 2 wind farms. But if you could somehow store that energy and say, whenever the wind blows, we're going to find a way to store that energy, and then when we need the energy, typically the next day in the middle of the afternoon, we're going to release that energy back onto the grid and use it when we need it. That's a huge need that the energy industry has. So most of the energy storage that's done right now is done by this process that might make you giggle a little bit. So they pump water up a hill, and then they let it run back down again. And when it runs down, they run it through a turbine. And so that is an energy loser, right? So if you think about this for a minute, you can't pump water up a hill and let it run back down again and expect to get more energy out of that process than it took you to pump the water up a hill. But because you pump it up at nighttime or at other times when you have excess energy and the cost of energy is very low, and it runs down the hill in the daytime when the cost of energy is quite high, the cost of generating energy is quite high, that process makes a lot of economic sense, even if it doesn't make any energy sense. So that's all 99% of the energy storage currently in the world is done that way. There are some other ideas about energy storage. But just to see how this would work, and then I'll tell you how the energy storage part of it works. So these are actual projected power demand. If you go through, this is in Southern California. This top line says this is the amount of power that we need, so that one of those lines is what we need, and the other one is what we were able to deliver. So we built this process in a model onto this grid, and the red line that you see down here is wind, and this is fairly, I just took a slice out of this. This is fairly typical wind, so it doesn't blow for quite a while. And then you get a big windstorm that comes through, and all of the windmills are producing a lot of wind, but they typically do it when you really don't need the power, on average. Sometimes they do it when you need the power, but on average they're more likely to do it at nighttime when you don't need the power than they are during the daytime. So this is our coal-fired power plant equipped with this technology. So the power plant has a capacity, and what happens is the power plant runs, and the power plant becomes the energy storage process. And so the reason that works is that to run this power plant, to run the energy storage, the carbon capture portion of this, all we need is some very cold refrigerant. And it turns out cold refrigerant is very easy to store, even if it's very, very cold. We do that all the time with liquefied natural gas. So if you make a big puddle, a big tank full of cold refrigerant at nighttime, more than you need to run the process, and then during the day, instead of using the 10% or 15% of the power plant that you need to run this process, you just use that cold refrigerant that you generated at nighttime. then 15% of the power plant goes back onto the grid. So you've effectively moved, at nighttime you've absorbed that energy, and in the daytime you've transferred it back onto the grid. And that's a very large amount of storage, because coal-fired power plants are very, very large. And so 15% of a power plant is a very large number. And because of some details, it actually stores closer to 45 to 50% of the capacity of the power plant that you can store, that you can shift back and forth on the grid. So in this case, we were able to, so what would normally happen is you'd have to have a bunch of very costly things. People, the utility company actually pays people to have power generating systems. They call them spinning reserves. We have, Mona is an example of that. If you drive down the highway, that's one of the spinning reserve locations that Pacific Corp has for generating power. So they have things that are just spinning and ready to generate power on a moment's notice, but they might not actually generate power for weeks, sometimes months, because the power demand doesn't get high enough for them to be dialed in. But you've still got to build them, and you've got to keep them spinning, ready to generate power, and that's extremely costly power. So anything that you build and only use for 3 or 4% of the year, or even 10% of the year, is going to be very, very costly. So, and so those get very expensive. But we don't need any spinning reserves in this case. So with this technology in the grid, we can absorb the energy and redispatch it the next day. We generate more refrigerant that we need when there's too much energy, and we drop the parasitic load by using the stored refrigerant when there's high demands for energy, and we can eliminate all that very costly spinning reserve. So we did the economic analysis on this, and the economics say that at least in Southern California, which is where these data come from, that we can actually pay for the carbon capture by the value of the energy storage. So they're essentially the same price. So a few other things, and I'll take some questions. This, just to emphasize to you how costly that gets, this is a price curve for how energy comes online. This one is in southeastern United States, but they take the cheapest generators, which are mostly hydro systems in this case, and then nuclear, and then coal, and they keep dispatching more and more sources of power until they get to the point where, and this is where the spinning reserves start coming in, and the cost of power for this last little increment here is extremely high. So if you can come up with a technology that can make this unnecessary, you can take that part of the curve out of here, you can have a big effect on the average cost of power, even by storing a relatively small amount of power. And so these are actual data from southeastern United States, a pretty dramatic shift in costs. So a couple of the other advantages of this technology is, as it removes the CO2, it turns out most of the nasty things that are in exhaust gases condense, most of them actually easier than CO2. So in the process of removing the CO2, we also remove essentially all of the SOx, essentially all of the NO. We actually remove so much mercury that there is less mercury in the exhaust coming out of this process, far less mercury in the exhaust coming out of this process than there is in the air that we breathe. So we're actually cleaning the air with respect to mercury. Removes almost all of the particulates. The only significant pollutant that isn't removed and is not significant in power plants, but it's a concern in general, is carbon monoxide. So all of the other pollutants are removed at the same time. So we can remove all of those pollutants also. Because of the increased efficiency of the process and the water we remove, we actually consume far less water than the other processes. So what is the state of the technology? I'll show you, go through a couple of slides quickly. So if you're an engineer, you can't just say that you remove things. So this is fairly typical operation where in this case, we're removing about 95% of the CO2 operating this process. This is the SO2 removal. That's actually the most expensive pollutant that we remove right now from flue gases. That's pretty difficult. You see it's removing at times over 100%. How does that happen? It happens because we remove so much of it that the instrument that we have that's trying to measure how much is left sometimes measures a negative number because it's essentially zero and it's just noise in the measurements. So in this case, it's 99.8% removal of the SO2. So the value proposition for this whole thing is we think we have a very energy efficient process. It's cost effective. It's a bolt-on technology. It's widely deployable. You can use it on natural gas power plants, oil refineries, cement kilns, coal-fired power plants, any source of CO2, any stationary source of CO2. It remains efficient at very high capture efficiencies, which is important in my mind. It's a multi-pollutant process, removes lots of pollutants. It captures the moisture, and it has this large energy storage component. So this is the nature of engineering. So we built this process a number of years ago, in what we call laboratory scale, so something roughly the size of this podium perhaps. And it was working great. So then we built it at what we call bench scale, so something that would sit in the front of this room, fill up most of the front of this room. So then we built one. We ran out of names for scale for this one, so we called it we named it Hyperion. It's named after one of the moons in the solar system that has the same surface temperature as this process has. So I work with a bunch of geeks, and so so we built that one, and then most recently we built 2 more processes, two other versions. So the equipment sits in 2 shipping containers, like you see on the back of flatbed trucks, and we have 2 versions of that. So each of them, one of them occupies 3 shipping containers, and the other one 2. And they're going around. They actually have caught. Both of them did their first realistic carbon capture here on campus from our heating plant and from some of the experimental facilities we have here. And now they're at power plants doing the capture there. So those are about $23 million items, and so and it's pretty big. You think about it. Shipping containers are pretty big. So when you walk around them, this is seriously big equipment. But we need to go. The next step is, so up until now, the sum of everything we've done up until now has been about $23 million. The next step alone will be about $25 million, where we'll build 7 shipping containers with stack them up on top of one another and make a true pilot scale facility. That'll be the equivalent of about a 5 megawatt power plant system. And then the next step will be roughly $250 million, and that will be the first commercial scale system that we operate. And we're hopeful that we can do that fairly soon. So we're learning a lot from what we're operating right now, and we've got a lot of enthusiastic supporters who are trying to help us to get this developed for commercial use. So I've done almost all of the talking, but I'd be happy to entertain any questions or any comments from anybody if you have any other.
Is there going to be any side effect to putting CO2 in the soil?
So what is the effect of injecting CO2 into the ground, or storing it in the ground, right? So if you inject CO2 in enhanced oil recovery into an oil well, so there is a concern. Let me back up a little bit. There is a concern that the CO2, if you pump it into the ground, will find some way to come out of the ground and come rushing out in a hurry, and that can be devastating. So this has happened not from storage of commercial CO2, but by natural processes. Most recently in 1986, I believe it was, in Cameroon at Lake Nyos. Lake Nyos is a very deep cratered lake, and it's deep enough that the CO2 actually accumulates at the bottom of the lake. And nobody's sure exactly what happened. They think maybe there was a landslide or something that happened and disturbed the lake, but it turned the whole lake over at one time, and it released a large quantity. All that CO2 that was at the bottom of the lake came to the top of the lake, and the CO2 is heavier than air, so it came out of the lake, rolled across the ground and down 2 valleys, and killed every living mammal in 2 communities. From just so CO2 isn't especially toxic, but when it displaces oxygen, then you get CO2 actually. So CO2 is not toxic like carbon monoxide, but you can tolerate up to about 2 or 3% CO2 before you start having serious problems. So people look at that and say, really, you're going to pump this CO2 into the ground, and how long is it going to take for it to burp back up and kill everyone? So let me just tell you that if you put this into a oil reservoir, for example, that oil has been in that reservoir, sealed in that reservoir with natural gas on top of it at high pressure for over 60 million years. And so that's a very, very safe place to store CO2. But there's not enough oil fields, even depleted oil fields, to put all this CO2. So another place you put it is in saline aquifers. So you pump it down into this saline aquifer, means it's just a saltwater aquifer, a brackish water aquifer. So we put it in freshwater aquifers, but freshwater is far too valuable to pump CO2 into. So, so you put it in saltwater aquifers, and if you do that right, and it's not difficult to do that right, but if you do that right, there's every reason to believe that it will be stored there safely for many, many centuries. It will stay there. It will eventually, after about 100 years, it will absorb into the water, turn the water essentially into soda pop, and it will just stay down there. You'll have this carbonated aquifer now that maybe, you know, 1,000,000 years from now somebody will discover and wonder what in the world, nastiest tasting soda they've ever had. So, so there are safe ways to store it. There are also some very poor ideas. So you can store it, and this works well. You could pump it into the ocean, deep into the ocean, and if you get it deep enough, it will actually flow to the very bottom of the ocean. Most people view that as a really bad idea. We actually have very little practical understanding of the ecosystems at the bottom of the ocean, but we're pretty sure that if you flood them with CO2, it's going to be devastating to them. So, so most people don't want to do that. Japan's the only place that's really seriously considering that anymore. There are several other places you can put small amounts of CO2, but for the most part, if we do enough to change the climate, it's going to end up in aquifers. So.
The one graph you showed of, I think you said it was in Georgia, showing the energy usage and the cost, and
right.
That spike on the end. Is that spike on the end, would it be possible to mitigate that by our usage habits?
So conservation is always the smartest and the cheapest way to save energy. So part of the answer to that is yes. You have to get people to actually do it, but that's a great thing to do. But you always need, so that tail will always be there. So if you don't have an energy storage system and you decrease your average consumption by 5%, you still have these fluctuations in demand that you have to be able to meet, and they're only going to come by occasionally. And so you have to be able, so you're inherently are going to have some equipment that's just sitting there waiting to generate power because you have these unexpected fluctuations in demand. So even if you decrease the average by a little bit, you're still going to have that big spike at the end. But if you have an energy storage system that can meet that fluctuation, then you can actually eliminate that big spike at the end. So.
And so you mentioned here that 15% parasitic load. So that's just for the removal of the CO2. How much would that grow if you were accounting for costs of actually sequestering?
So that actually includes both. So that's the so the cost, the economic cost of sequestering is fairly small, but a big fraction of the energy that you use is for these other processes. A big fraction of the energy that they use is the energy required to compress the CO2 up to the pressures that you need to be able to sequester it. So.
Can you say a little bit more about mercury and coal burning power plants and seeing methyl mercury in the food chain? In fact, in cord blood, it's going up in infants born in Salt Lake City. Methyl mercury. Can you say a little bit more?
Sure.
About removing that?
Sure. So first, let me give you the perspective of mercury. So coal is not saturated in mercury. Coal has less mercury in it on average than the average, probably the average 50-year-old human being has. All right. So most of us have dental work that included mercury amalgams. It's just that we consume so much coal and burn so much coal that the very small amount of mercury that's in coal has no more mercury in it than dirt or anything else. But we don't burn 2 billion tons of dirt a year in the United States. We do burn that much coal. So coal is the principal contributor, man-caused contributor of mercury in the atmosphere. About 30% of the total mercury and over 50% of the man-caused contribution comes from coal, or from fossil fuels in general, mostly coal. So this process, as you cool this flue gas down, this process, long before you condense any CO2, this process will have condensed all of the mercury in the flue gas that the coal contributed. And the only mercury that will be left is the mercury that came into the flue gas in the atmosphere. So the air that we breathe has about 1 part per billion mercury in it. So, and that's just, it always has had, that's just the natural background of air. So you actually get to the point where you've collected all the mercury from the coal at about a negative 40 degrees. We've got to go to a negative 130. So as you continue to cool the gases down, you're collecting mercury that effectively came from the atmosphere, not from the coal. And by the time you're at the end of the process, you've captured 99.97% of the mercury that was in the air and all of the mercury that was in the coal in this process. So it will remove mercury and most of the other pollutants much better than the current technologies that we used to treat those systems. So we're almost out of time, but I'll be happy to take maybe one or two.
So you said you have like a couple more steps until you get to commercial scale. What would you predict is your timeline until you actually get to a commercial scale?
So we hope to be building the commercial scale system in 2017. So a lot of that will depend upon how good of engineers we are and the cooperation of sponsors to get us through these fairly expensive steps. So one more hand in.
I know this is difficult to answer because there's so many variables, but roughly how much per ton of CO2 would this cost?
So with our process, so it is difficult to answer, but it's one of the things we have to answer all the time. So we've been through this analysis many, many times. So we can, but we are quite deliberately conservative in the numbers we say. So for public consumption, we say that we can do this at $35 a ton. We can capture CO2 at $35 a ton. The actual number is $24 a ton. That's what it comes out to be. But we haven't actually built the commercial system yet, and there are always some surprises.
That's at the 95% level?
That's at the 90% level. So at the 99% level, that would go up, but only slightly. So you can sell CO2 right now to oil producers, for example, for $40 a ton. So you could actually make money on this if you put it in the right place and sell the CO2 to someone who can consume very large quantities of CO2, which oil producers do. So, but that's still a lot of money. So I don't want to kid anybody that this is a small investment. This is the industry that is eventually going to do this, and if we don't do this, we are looking at devastating, I think, consequences to the planet. It's an enormous industry, and it's one of the few times in life there's an industry, half the size, a third of the size of the entire oil industry, entire energy industry, and right now there are 0 players in it. So, and it's something that we need to do rapidly. But mostly it's going to be driven by regulation. There are going to be relatively few opportunities to actually make money capturing carbon. You're going to do it because you're forced to do it in order to generate electrical power. So happy to talk to anybody else up here, but we've taken 55 of our 50 minutes. So appreciate the chance to talk with you, and excited about the consequences.